Good morning or good afternoon, wherever you are in the world. So my name is Ella Cranmer, and we're going to present our work that I've been doing with my colleague Ernest. So in our work, we're exploring how we can make AR systems more dependable. So dependability in this context, really, we're looking at reliability, safety, and availability. So if we go to the next slide, please. So just a brief introduction to ourselves. So we're both part of the Department of Operations, Technology, Events and Hospitality Management at the Business School at Manchester Metropolitan University. So I did my PhD also at the university, where I was exploring augmented reality in the tourism context, coming up with a business model looking at how we could implement the technology for value from multi-stakeholder perspective. I'm also part of the Creative Augmented and Virtual Reality Hub. We've done various different projects in AR, VR, mixed reality and other emerging technologies in different contexts, and worked on some projects with various different companies. And we're also involved in organising the International AR and VR Conference, which for the 5th time last year is where we presented this research in Munich. We've got one coming up in June this year in Lisbon. So over to you, Ernest, to introduce yourself.
Yes, so I'm Ernest 34, and as Ella said, we are in the OTM department here at Manchester Met. My research interests usually center around reliability engineering, because that's what I did my PhD in, and I've been furthering that research till now. I teach various units at the university here, but usually it's around programming with Python or web design and things around those areas. And I'm also the program leader for the apprenticeship program in the department.
Okay, so if we can go on to the next slide, please. So very briefly, just to tell you what we're going to be talking about. So firstly, we'll talk about why we've embarked on this research journey and kind of how we see where this fits with the current kind of economic environment. Then the research questions that we've been exploring, and we'll talk a bit about a case study that we've looked at and demonstrate the application of our techniques. And then it will be open to discussion, where we'll talk about what our aims are for the future and maybe how we can explore some collaboration opportunities. Next slide, please. Okay, so as we all know what augmented reality is, and it's used, and there's many various applications, a lot of which normally tend to be quite low risk. So whether that's for a navigation aid in a tourism context, or to add more engaging content in educational tools. As AR systems are becoming more popular, they're more integral to systems due to the different benefits they provide, which I'm sure we're all familiar with. But we're really interested in looking now at how we can use and explore AR to improve information visualization in different high-risk environments, and how we can start to minimize some of the risks, especially in environments where there are high consequences. And you know, we need to make sure that the safety, for example, is key. So in healthcare, there's a few studies that have researched and found that AR can be helped with training to decrease risks in visualization of the anatomy and things like that, which can lead to increased patient safety, reduction in costs, and eventually, hopefully, to save lives. So as AR systems are developing and progressing, the hardware, the software, the human interaction, and all the different elements, there can be numerous different points of failure. So in a safety critical system, these failures can have catastrophic and very high impact consequences. So this places big significant importance on the dependability analysis. So our research, simply put, is to explore how we can perform a detailed dependability analysis of AR ecosystems before implementation to hopefully avoid some of these risks and these catastrophic consequences. So now over to Ernest to explain a bit more about what we've done so far.
Next slide, please, Angela. Right, so as Ella mentioned, an AR ecosystem is not just the AR device. You've got quite a lot of components or subsystems coming into play. You would have hardware, software, humans, and probably other systems come into play, sometimes span over a wider geographic area. And therefore, the dependability of just the AR device is not sufficient to determine the dependability of the entire system. A comprehensive dependability analysis of the entire system is required to provide useful information on reliability, safety, availability of the system. Now, these metrics are what we would be calling dependability analysis, or which constitute dependability analysis in this research. Reliability is basically the ability of a system to function as intended. Safety is the ability of a system not to cause harm to people or to the environment, and availability is basically the ability of a system to function as intended when it is required to do so. Next slide, please. So what we started working on about a year and a half ago was actually to come up with a framework to help in providing a way of analyzing systems before they actually implemented. That's AR system before they are implemented in high consequence environments. And we thought of doing it in 3 stages. One is the modeling stage. First of all, we have to identify the risk drivers and how they relate with each other. Then we classify them to understand their behavior. Then we will then translate them into a temporal fault tree, which I'll be talking about in a moment. Once we have the fault tree, we can perform what we call the logical analysis, which is understanding how these components relate to cause a total system failure. So we have various risk drivers. How do these risk drivers relate? That's the combination of the risk drivers to actually then cause a total system failure. Once we've had that, we can then create what we call an efficient configuration of the system, which in technical terms will be a minimal cut set or minimal cut sequence. With a minimal cut set or minimal cut sequence, then we can move on to perform some probabilistic analysis, which is more quantitative. So then we can evaluate the reliability, the availability, maintainability, security, safety, and other measures from that. But we will focus on the 3 I mentioned earlier, which is reliability, safety, and availability. We're going to use Monte Carlo simulation, and I'll talk about why we're going to do that in a minute to evaluate these measures. Next slide, please. The 2 main techniques you're going to use are fault tree analysis and Monte Carlo simulation. So I thought I'll give a very quick overview of how fault tree analysis works. So what we have in front of us is a very simple redundant system, power system, where you have a primary source of power, which is the mains, the electricity mains, and we have the secondary power source, which is the generator. We also have a sensor which will detect an emission and sort of activate the generator if there is an emission from the E. So would you hit the next slide, please? So then if the system is turned on, that there is a demand, which is from the bulb, which is a medical device, then the power will flow from the from the E to deliver the service needed by the medical device. However, could you hit the next slide, please? However, if there is a fault, then could you hit the next slide, please? Then the sensor would activate the generator to provide the necessary energy needed. So then there is no fault, the system continues to work. Next slide, please. But if there is a fault between the generator and the battery as well, then of course the whole system fails. Now with fault tree analysis, what you usually want to do is you first of all consider what you call the top events, which is the system, an undesired state of the system. Now, if we say the undesired state of the system is the bulb failing, we want to ask ourselves, what can cause the bulb to fail? Next slide, please. One, it could be if the generator has failed or the electricity has failed. Of course, if the 2 power sources have failed, then there won't be any electricity. Slide, please. Also, if the bulb is broken, then of course there won't be any light as well. Next slide, please. And we also have the switch. If the switch is broken, failed, then there won't be any electricity as well. Next slide, please. One would say if the mains is broken and the sensor is broken as well, we won't have electricity, but that is not accurate, because if the sensor fails before the electricity, there won't be any power. However, if the electricity fails before the sensor, there would be power. Meaning, if the electricity fails, immediately it fails, the sensor hasn't failed, so it activates the generator to provide the necessary energy, and we have power. If it's the reverse way, that's if the sensor fails before the electricity, immediately the electricity fails, the sensor has already failed, so it is unable to activate the generator to provide the power. So dynamic fault trees actually consider the sequences in which events occur to sort of produce an accurate evaluation of the system. Next slide, please. Yeah, so we've seen fault analysis, and we also want to use the GoldSim software in the quantitative analysis. Now, before we talk about even the GoldSim software, we want to talk about the qualitative analysis, which is the logical analysis, which we haven't pointed out here. We're going to use what we call the temporal logic trees to actually minimize the system into its efficient configuration before we use GoldSim. GoldSim is basically for quantitative analysis. We chose GoldSim because it has a way of capturing real-world events, and not just ordinary real-world events, very, very complex real-world events. It can also capture any system with any sort of failure distribution, exponential distribution, variable distribution, log normal distribution, and name it. It's also useful for capturing various system data as well. So you can capture failure data, you can capture repair data, you can capture maintenance data, preventive maintenance, replacement data, and so on and so forth. And you can capture other system operating environment data as well. For example, the flow rate or withdrawal rate, or things that has to do with the system, time of operation. So we thought that would be an amazing tool to do it. And it uses Monte Carlo simulation, which is a way of simulating the behavior of a system, that's the future behavior of a system, using random numbers to represent the variables in the system. Next slide, please. So last year we did a simple case study with this image in front of us, which is taken from an article in the journal Nature. What's happening here is we have a clinician who would use an AR device to perform a surgery on people's jaws. What happens is we have a CT scan which has a scan of various things, and you have markers on the jaw. So then the AR device projects some of the scans onto the markers on the jaw. The clinician knows exactly where they are because they have the markers, and then they can successfully perform the operation. What this didn't have is it didn't have any sort of analysis on how reliable the system is. So we thought, well, because we've come up with this framework, let's apply it to this system and see if we can make any sense of it. So we did so, but we had to, next slide please, we had to come up with our own sort of failure data. So we have some failure data here. The connection media is basically the medium through which the devices are connected. So it could be through wire, it could be through the internet or Bluetooth or whatever connection media. We've given it some failure data as well. So the failure data is exponentially distributed, and it's got a mean delay until repair to be 2 days. Now, of course, for a medical device, for 2 days, having 2 days as a mean delay until repair time is not, it's not acceptable. You'd want to change that, but I'll talk about that when we come to the results bit. We've got the tracker as well. We've given it some failure data. We've got the mixer. We've given it some failure data. The headset, we've given it 2 sorts of data. One is the power failure. The other is preventive maintenance every 3 months. The power as well, we've given it some failure data. We've given it quite a number of various failure data as well. So we have the subsystem failure. We have the internal power failure, and so on and so forth, which I'm going to go into in a minute. Now, the mu's and the omegas are the scale and shape parameter of the variable distribution, and the lambda is the hazard function, and the others are for log normal distribution, the mean and standard deviation of log normal distribution. Right. Next slide, please. So what we did was, after we did that, we did the logical analysis with another framework which we haven't talked about, but that we did manually. And then we modeled everything in GoldSim. Now you can see the components here are isolated, so the tracker, connection, headset, mixer, power system, they are all isolated, but actually they are connected, which is not shown on the slide. So they are all connected using logic gates, which is like ANDs and ORs and things like that. And we've also modeled the power system. So we have the same sort of power system I described a few minutes ago: main source of power, standby source of power, and a controller that detects an omission or a failure in the primary and activates the standby. So we did that, put the failure data in, and we ran the system a number of times. Next slide, please. So we ran the system to sort of, we use a lifetime of 100 days and a time step of 1 day, and we did 1,000 iterations per day. Once we did that, we had these results. Now the purple line underneath is actually overlaying a red line. So I have to say that. So there's a red line underneath the purple line. So what we have is a graph of availability per time. So we can see that at day 1, the system was, well, between day 0 and day 1, the system was reliable, which is very good. But then as we approach 100 days, the reliability falls, which is what you would expect. The overall reliability falls, which is what you would expect. Here it shows that the power system actually is the least reliable of them all, and the system is actually not reliable because the system's reliability and the power system overlap. For a medical system, that is not good enough. You want everything right at the top. One interesting thing we can see is on the right in the table there, we have fail, rel, and the con. The cons is actually for contribution to system failure. You can see that the mixer actually contributes most to the system failure than the power system. Even though the power system is the least reliable, it doesn't contribute as much to the system failure as the mixer would. So what you would want to do with this data then is to sort of have a more reliable mixer by buying probably a more durable or a mixer that's more reliable, and also bumping the reliability of the power. Once these two have been done, hopefully to move the whole system reliability up, and they will all be up there. So that's something we can deduce from the data, and even a lot more. We have a book chapter on this, which is coming out in the next few months, probably a couple of months, and we have all the detailed analysis there. So if you're interested, you can have a look, or you can ask us and we can point you in the right direction for the book chapter as well. Next slide, please. So then after doing this, we then met area, and for us, area has been a sort of because we went through some of the documents area has got, and in the barriers to adoption, I think there are 3 barriers to adoption. One of them is safety. We were marrying that with the area schema of needs, and we realized that where our research sits is the safety area, and so we want to sort of delve deeper into that. We don't know comprehensively what has been done, so we would want to know if, say, people are working in this area, and then we can see where we can sort of collaborate in that sense. What we want to do basically is to create a framework for identification, classification, and measuring of risk drivers, which I talked about earlier. Now we stand at a point where we want a real-world case study. So if there is any sort of industry or company here who are hoping to work on a real-world case study and they are interested, we are more than happy to sort of collaborate and see if we can come up with a framework to help in that area. If there are things going on as well, and that maybe you think, oh, a lot has gone on, these guys are not up to date, we would want you to sort of nudge us as well, so we can, so you can point us in the right direction to move this research forward. And is there anything else I've missed? Looking at time. No. Yeah, so that is us. Next slide, please. Thank you, and any questions? Is everyone there?
Right, should we open it up? Any questions, comments?
So I guess
Mark, anything?
one question we have then maybe is what do you think the main concerns are with regards to safety in the sectors that you're working in?
Hi, this is Mark. I don't know if Gary or Greg or anyone who are actually implementing some AR solutions, maybe just talk a little bit about where you see some of the safety, biggest safety risks.
Hi, Mark. It's Gary Smith here from Duckery Washwater in the UK.
Hi, Gary.
Can you hear me? Can you hear me?
Yes, we can hear, Gary.
Okay. Hi, guys. Yeah, really interesting presentation. Thank you. It's nice to see some local talent as well being developed. So we presented at AWE in Europe in Munich on some of the risks and controls that we're trying to now wrestle with in our AR rollout really within Welsh Water, and actually some of the that you talked about really landed at home. But for us, sort of some of your failure modes in terms of power or hardware failure sort of pale into insignificance in respect to some of the really quite high risk environments that operators are working in. So if you were to score the risk of power failure, for example, it would be fairly low. But actually working in a hazardous environment, an explosive atmosphere, or in a dark environment where there's a risk of flooding, sort of skews your calculations a little bit. So you said you were interested in talking to people where they got real world applications. Well, certainly that's something we'd be quite happy to do with and share some of the learning we've had in that sort of environment.
Oh, fantastic. That's great.
Yeah, that would be great. Thank you.
In fact, that's one thing we are keen on sort of doing, because what we did was we didn't have any sort of real data. So these were all sort of hypothetical. Even though the case study was real, the data itself, we didn't have any access to data. So yes, we'll be more than happy to explore this further and get some real data to work with. That'll be very useful.
Yeah.
I can take an action to just connect you up with Gary and anyone else.
That would be great. Thank you.
This is Brian. I'd be happy to share with you guys too. I work for the Boeing Company. I'm a technical fellow and a PhD in human factor psych. And some of the things that we found were kind of interesting. We were doing the wiring for the 767 tanker that ended up working out better than we had anticipated. Was that one of the things that was interesting, that the mechanics, when they would first put on the HoloLens headset, they would turn the brightness up all the way and put the thing on, and then kind of get their bearings and see where everything was at. And then they would turn it down almost completely. So they wanted this just the barest minimum of kind of a just noticeable difference, if you will, so that it didn't include their hands as they were doing work. So there's a lot of things like that that we found that were interesting. Like, you probably are aware, I've had some knockdown dragouts with some folks, and it seems like the less they know, the louder they scream. But a lot of people would come at me and say, oh, well, it's not 4K, and all this stuff, and talk about fidelity. And it's like, well, what we've actually found when you're doing this stuff is that they don't really want high fidelity. They want, they want to have a suggestion of where these things go, in respect to each other and spatially registered. But if you have too much fidelity or too much brightness, it actually distracts from them being able to do meaningful work. So there's a lot of little kind of things like that we learn firsthand from doing it out in the factory that may not be necessarily intuitive to most folks.
Yeah.
Right.
In particular, like doing the wiring stuff on the planes is hazardous in particular because it's a very noisy environment. In the case of the 767, we're taking about 2.5 times the wiring and putting in 1 times the plane, so it's really visually complex. There's a lot of stuff going on, And they also, as they're doing this work, a lot of times there'll be floor panels that will be missing. And so
Wow.
there's a lot of attentional, yeah. So you can imagine how, in fact, at one point we put this on an individual and he was kind of so overwhelmed by it. He started to kind of running around trying to investigate, what he was seeing visually. And I was pretty concerned about to spot this guy sufficiently so that we didn't have a safety issue where he fell through the floor of the plane. So it's interesting. There's just a lot to it, a lot to unpack, but happy to have some follow-on discussions if you guys are interested.
So just quick, are they using the HoloLens then to show them where certain wires go and things like that?
Yeah.
If I understood that correctly. Okay.
Yes.
So have you found that that's been more accurate than how they were doing previously?
So we were multi-fold over on labor because, well, going into this, right, we were behind schedule, lots of issues because we're trying to basically take and meld kind of older airframe technology with newer, tanker technology, boom technology stuff. So we had again, 2.5 times the wiring and 1 times the plane. It's almost like, and then you have all these different subsystems that have to interact to some degree. And so it's kind of like doing an archaeological dig in technology, relative to the engineering. So there's a lot of issues there. And then in addition to that, we were looking at a many-fold overage on labor, and our first pass yield was less than 50%. It was not good. And largely it's because the complexity of the environment that we're dealing with. I mean, these people, there's no, first of all, that when they go to do the work, they have to do a bit of research before they go and actually do the work.
Yes.
And so they would go and pull the drawings. Well, the drawings have been so corrected and recorrected, and there's just a lot of changes. So when they print these things off, they're literally 20 plus feet long in terms of a contiguous piece of paper on a plotter. And then they have to take their Sharpie and they have to go through and look at all this myriad of drawings. And it'd be bad enough if it was one contiguous picture of the wiring loom, which would look like a rat nest of spaghetti, but it's even worse than that because it's a bunch of chopped up sectional views of that wiring. And they do that because every time somebody, requests a new view of that loom, then they add it to the drawing collection. So they have to take their little Sharpie or their little highlighter and go through and look at all this myriad of drawings and figure out, well, I have this particular wiring loom, which of these pertains to what I'm going to try to do. So they go mark all these up, and then they don't have any place to unscroll this on the plane. So I have to chop that up into like an 8.5 by 11 book, right? So it looks like a phone book, and they walk on there on the plane, and then they have to flip back and forth very quickly between these drawings as they try to assemble this mental model in their head. And you guys don't really understand this, right? So we don't have very good length of a working memory. So they're trying to imagine this and then keep that fresh in their mind and simultaneously mind the parts that they're going to install, their tools, where they're at, are there panels missing in the, I mean, we can go in, I'm probably, we can talk about later, but it's just ridiculous, right? So at the end of doing the prototype, they successfully, we put it on there. We went from many fold over on labor hours to cutting the overall takt time by over 50%, which is ridiculous. And what's even more telling, in my opinion, was that we went from, over 50%, less than a 50% first pass yield to 100%. We had 0 mistakes.
Wow.
And this is on the first pass. Like I would not expect that. So
yeah, it'd be great to have a chat outside of this and find out more.
Yeah, and I say that all with caution because this is a preliminary thing, and so would that pervade? I mean, is there a Hawthorne effect? I mean, there's just a bunch of things that we would have to consider in this. But so we're still kind of preliminary, and we're rolling it out farther within Boeing. But the results were beyond what I could have expected. Like I couldn't make up stuff as good as this kind of turned out. When we another surprising thing is we expected the older mechanics. There's kind of this layperson's myth that the kids, the young whippersnappers, they'll take to it, and the old folks, like, they're gonna revolt and say, no, I don't want to do that. And we actually found in some ways that the older folks actually seemed to have more of an appreciation because they really understood the difference between how they had to do it in the past and what the new process could be. and where the younger folks were kind of a little less plussed by it because they're kind of like, yeah, nah, whatever. You know, I mean, they're used to Fortnite, you know, a lot of virtual things, and so it wasn't as novel to them, I think, is probably what we were seeing. But we actually had a lot more embraced by older mechanics that I initially would not have probably expected. It was kind of interesting.
Yeah, it is. We'll have to have a chat.
Yeah.
Yeah.
Yeah. So in terms of in practical terms, I mean, this goes to anyone. Would dependability analysis be useful in your sector? I know some of you are working in high-risk environments, some aren't, but is it something that would be useful in your sector?
Yeah, this is Greg with Boeing. I think it's very possible, you know, that we could look at co-opting some of this for additional hazard identification purposes. Again, you know, something that I think, you know, you and I and Brian could you know, meet on the side and look over and discuss.
Yeah.
Yes. Yes.
So, because I think we've got a little bit short time here. I think we got a few more things on the agenda. If that's okay, you know, we can kind of move forward.
Yeah.
That's right. Perfect. So, yeah, we've got your contact information, and Brian and I can, you know, work out when a good time for us to kind of chat off the side.
Yes.
Yes.
Yes. That's brilliant. Thank you. Thanks.
Thank you.
Sure. Perfect. Thanks. Appreciate the
Good job.
presentation. It's great.
Thank you very much for your
Yes.
input.
Thank you all. Mm.
Thanks very much, guys. Thank you.
Thank you. We'll be in touch soon then.